In this chapter, the problems I'm going to be doing are going to accompany the chapter on periodic trends. In this chapter, what we're going to be learning about is the trends of the elements on the periodic tables. And instead of memorizing a whole bunch of facts about the periodic table, we're going to memorize, or we're going to look at the trends and try to understand the trends both chemically and physically. First thing we're going to be doing is we're going to be looking at electron configuration. So this happens to be electron configuration. The number here, the 1, 2, and 3 are going to represent the principal quantum numbers. S is going to be the type of orbital, and the superscripts are going to be the number of electrons in that orbital. So to start out with, the first question states, the following electron configurations represent excited states. That means that they're not ground state. They're not going to match up with the periodic table. Identify the element and write its ground state condensed electron configuration. These are really pretty easy to identify the elements. So we're going to look at, there are 7 electrons, and since these are all neutral, they might be in the ground state, but they're all going to be neutral. We can simply just write, we know that they're going to be neutral, so the number of protons is going to be equal to the number of electrons. So since there are 7 electrons here, there has to be 7 protons. So therefore, this tells us that this is the 7th element, and that's going to be fluorine. Fluorine is going to be the 7th element. Now, if we write the ground state electron configuration, that's going to be 1s2, 2s2, 2p5. Right, that's the ground state electron configuration for fluorine. For the next one, we have argon. So this is the condensed, meaning you go up to argon, right? You go to the, basically in essence, you start at the noble gas and then you work from there. So whatever element you're looking for, if you happen to write if you need to write the condensed electron configuration, you'll see what I mean. We'll do it for this one. But here we have 1, 2, 4, we have 14. So we want to look at the 14th element after argon. If we look at that, that's going to be germanium. Germanium is the 14th element after argon. And so we want to write the ground state electron configuration for this. And that's going to be argon. And then it's 4s2, 3d10, and then 4p2. So in pink is going to be the ground state electron configuration. For the next one, we have krypton. Let me get back to the condensed state here. If we want to write the condensed electron configuration, you look at germanium, look at where it is on the periodic table, go backwards till you come up to the noble gas, and then go forward until you come to germanium. So here we have krypton, and this is going to be the 7th element after krypton, and that is niobium. I'll just write that out for you. It's one we don't talk about a whole lot. Now, if you write the ground state electron configuration for this in the condensed state, you're going to start out with krypton, and it's going to be 5s2, 3d3. Oops, not 3d3, my fault. That should be 4d3. Sorry. 4d3. All right? In this problem, what we're going to be doing is we're actually going to be coming up with the electron configurations for the following elements. So write the condensed electron configurations for the following atoms using the appropriate noble gas abbreviations. So for the first one, we are going to be dealing with cesium. So what you do is you go backwards from cesium and you go to the noble gas and you write the closest noble gas to it. And in that case, that's going to be xenon. Now you then go forward, so you start at xenon, and then you go to cesium, which is going to be 6s1. For nickel, the previous noble gas just prior to nickel is going to be argon. And then you go forward from that, and that's going to be 4s2, 3d8. Selenium, you start at the noble gas prior to that, and that likewise is going to be argon. And you start at argon, and you go till you get to selenium, and that's going to be 4s2, 3 4d10, 4p4. All right, 4p4. We'll see if this marker has any more life left in it. Cadmium, you go to the noble gas before cadmium, and that's going to be krypton. You start at krypton. All right, start krypton, and you go forward, which is going to be 5s2, 4d10. That one's done. Uranium. Uranium's a hard one. You start at radon. You start at radon, and you go 7s2, 6d1, 5f3. You got to see where the F group slips in just after 6d1. All right. And then lead, you start the noble gas prior to that, and that's going to be xenon. Then it becomes 4f14, and then it is 6s2, 5d10, then it becomes 6p2. All right, so that's how you come up with the electron configurations for the following elements. If you have any other questions, please let me know. In this question, it states which neutral atom is isoelectronic with each of the following ions. So isoelectronic means the exact same charge. And these are really simple. They're really simple to think about. So if we look at gallium 3+, gallium 3+ means I had to give up 3 electrons. The element that's going to be isoelectronic, which means it's going to have a neutral charge, add the gallium 3+, you simply start at gallium and you go backwards 3 because it gave up 3 electrons. So you go backwards 3. And if you go backwards 3, you end up with nickel. So if gallium gives up 3 electrons, it will have the exact same electron configuration as nickel neutral. All right. Zirconium 4+, you start at zirconium, it gives up 4 electrons, and so it's going to have the exact same electron configuration as rubidium, being neutral. Manganese 7+, if it gives up 7 electrons, it's going to have the exact same electron configuration as neutral argon. Iodine. Iodine's a little different in that it's gaining an electron. So you start at iodine, you give it 1 more electron, and it will have the exact same electron configuration as xenon, because xenon has 1 more electron than iodine neutral. And so if you give iodine 1 electron, it's as if you have the exact same electron configuration as xenon. Not number of protons, but the exact same electron configuration. And with lead, you lose 2 electrons, it's going to have the exact same electron configuration as mercury. All right, so these are pretty simple. It's not that hard. If you have any questions, let me know. In this question, it's going to be referring to ionization energy. What ionization energy is, it's the ability of an atom to give up an electron. So, and if it's going to give up an electron, it's going to become a cation. So this is the ability of an atom to give up an electron to produce a cation. And remember, as you go down the periodic table, the ionization energy is going to decrease, meaning it's easier for those elements to ionize. As you're going from left to right, the ionization energy is going to increase, meaning it's going to be much more difficult for it to ionize. So it will have a higher ionization energy. So what we have up here is we have 5 examples. Each example is going to have 2 different elements. We need to figure out which one is going to have which will have the smaller first ionization energy. So we're trying to circle the one that has the smallest first ionization energy. So the first example we have is chlorine and argon. And the answer, one that's got the lowest ionization energy, is going to be chlorine. And the reason being is it is to the left of argon. It's going to be to the left. So as you get going from right to left, the ionization energy is going to decrease, meaning it's going to be much easier to form an ion or a cation. Argon obviously is going to have a full octet. It certainly isn't going to want to give up an electron. But chlorine isn't going to want to give up one either, but it'll be much more readily to give one up than, say, argon, which already has a full octet. The next one's going to be beryllium and calcium. And calcium is going to have the lowest ionization energy. And the reason being is it is lower than beryllium on the periodic table. The next example we have potassium and cobalt. And potassium is going to be to the left of cobalt, and thus it's going to have a lower ionization energy. The next one, D, is sulfur and germanium. And germanium is going to have the lowest ionization energy because it's down and to the left, my left, I'm left-handed, remember, to the left of sulfur. For E, we have tin and tellurium, and tin is going to have the lowest ionization energy because it's going to be to the left of tellurium. All right. If you have any questions on this chapter, which is dealing with periodic trends, you are more than welcome to ask me, and I will certainly entertain any questions you have. Have a good day.